Yeah, let's consider this particular circuit to understand what node analysis is. Let me tell you, when we were doing mesh analysis, we were interested in what? We were interested in identifying the meshes and marking the mesh currents. Everybody understand that? See here, if we go to mesh analysis, see, we used to see how many meshes are there and we used to mark mesh currents. There are two meshes, so we mark two mesh currents. Why were we doing that? Why were we doing mesh analysis? To find the mesh currents. How did we used to find out mesh currents? By applying KVL to each mesh, isn't it? And another thing that you need to know in this circuit is not to every mesh we apply the KVL. We don't apply KVL to all the meshes available. Okay, so we need to be good in analyzing the circuit. What is the knowledge that we needed when we were applying the KVL here? We said this KVL is applied to find the mesh current. So when we know the mesh current, we don't apply the KVL to that particular mesh. Suppose this is mesh 1, right? In mesh 1, we know the current I1 is 2.5 milliamperes. And in mesh 2, I2 is there, but I2 is not known. So since I1 is known, I don't apply KVL here. Since I2 is not known, I apply KVL here. Though there are two measures, it's a one KVL problem. It's one KVL problem. Understand that? So again, I'm repeating, in mesh analysis, we apply KVL to find out the mesh currents. Okay, but if the mesh current is known, there we don't apply the KVL. Now, let's come to the node analysis. Okay. Now, there are how many nodes? Nodes, what did I say? Two or more branches should come together. Two or more branches should come together, and that point where two or more branches come together is a node. This can be a node. When could this be a node? When I consider this R1 as a separate branch and the voltage source where it is connected, that as a separate branch. Okay, so yesterday I was showing you that. Suppose your circuit is like this. The same circuit I have taken here. See, AB you can consider as one branch. Then the branch where this is, that also can be considered as one separate branch. That is, if you're doing that, then A has to be marked. If you're not considering that, see this B, add B to this particular point. So this is one branch you can consider. See, this is how the circuit is. If you write it, the same thing can be written in this way. So that means marking A and D is not necessary. Another thing that we can see is when I mark A, suppose everybody understand this. If you have knowledge, just share with me. Okay, see here. Suppose if I mark this as 5 volts, okay, this is node A, right? Do you know what is VA? Voltage at node A. Anybody? This point is ground. This point is ground, mind you. See, this is all ground points. This is all ground. Okay. So can you tell me what is voltage VA? What is voltage? VA is the voltage at node A. Okay. So that means voltage at node A is 5 volts. Why? Because between node A and this ground, there is 5 volt source connected. That's why the voltage at node A is 5 volts. So when I know the node voltage at A, I don't again apply KVL there. I am not interested in marking it over there. Similarly here, see here, yeah. Suppose if I mark this as node say 1, okay, what is our V1 here at node 1? V1 is VA, so V1 is known. So I'm not interested in marking the nodes where I know the node voltages. So that is one thing. So that's why what I would rather do is I don't go for marking these as nodes. Let's see, I'll just show you. See here, this is node number 1, 2, 3, 4, and this is ground. This is the fifth node. Okay. Among these 5 nodes, which are important to me, let me take at node 1. At node 1, okay, voltage is known, that is VA known. At node 2, sorry, at node 4 rather, at node 4, what do we know? We know V4. At node 4, the voltage is V4. At node 1, the voltage is V1, like this. Okay. So what is V4? Can anybody tell me? What is V4? Here, V1 is VA, but V4 is minus VB. Why it is minus VB? See, plus is connected to the ground and minus is connected to node 4. So you need to be a little careful regarding this. So V4 is minus VB. Everybody understand that? Okay. Now. So when this is also known, this is also known. Okay. So what is the idea is when node voltages are known, when node voltages are known, no need to mark the nodes. No need to mark the nodes. Everybody understand this? So this is something one needs to remember. Get that point? So since we know V1 and V2, V1 and V4, it's not necessary we apply nodes there. Something to remember. So how do I like to have this circuit as? Let me take this. Yeah. How do I want this to be? Therefore, what I do, just look at this. Therefore, what do? I don't want these and this. Okay. So rather, what I want, I'll just write that once again. I don't want to name them as 4V1 and all. Okay. So how do I want it now? Is what we need to look at. Okay. So what I want is this. Everybody look at this. Let me make this as R1 first. This is R2. Okay. Now let me join this. I'll call this is my node 1. Okay. At node 1, I'll mark the voltage as V1. This is my node 2. I'll mark the voltage as V2. This is my node 3. Okay. And I don't want to name it. This is my node 3. I know the voltage at node 3 is 0 volt. That's why I don't want to mark it. Understand this? So this is the scenario. Everybody is okay with this? How many nodes are there? There are 3 nodes. There are actually 1, 2, 3, 4, 5 nodes. But this node and this node I don't want to consider because at those nodes I know the voltage. Or in other words, I'll consider this R1 and VA as one branch and R3 and VB to be in another branch. So that's why I'm not interested in marking these as my nodes. Okay, so this anyways is a node. So what is the difference between node 1 and node 2? See here, these two nodes are called as non-reference nodes. Non-reference nodes. Okay, and this is called as reference node. Reference node. And we apply KVL only to these non-reference nodes. KCL rather, sorry, not KVL. It's KCL now because it is node analysis. Here, no KCL. No KCL. Why no KCL? Since the voltage is known. The voltage is 0 volts. That's known. Get this point, everybody? Okay. Now, let's consider this circuit and let's see how to apply KCL now. Okay, so wherever we want to know we want to know what is this V1. I want to find this voltage at node 1. I want to find the voltage at node 2. And when you say you're applying KCL, you're applying KCL at node 1, not at V1. You're not applying KCL at V1, mind. You're applying KCL at node 1, applying KCL at node 2. We don't apply KCL at reference nodes. Okay, we only apply KCLs at non-reference nodes. Understand this? Okay, and what type of circuit is this? What type of circuit we used to call this in mesh analysis? This is type 1 circuit. Why this is type 1 circuit? Because there is no current source. Everybody understand that there is no current source. That's why we were referring to this as the what type 1 circuit. Now let's again take the same circuit. Let's see how to apply KCL. Now let's understand how to apply KCL. Okay, now let's do this. Again, I want the circuit. Now, whatever circuit you have, you can just start dealing with it. Okay, how to apply KCL at node 1 and node 2. Let's see. Fine. R1, R2, R3. Okay, and I don't want these. Fine. So this is something. Yeah. Okay. Now this is, let me say this is V1 and V2. So this is type 1 circuit. Let's consider this as type 1 circuit. What is this? Type 1 circuit. Why this is type 1 circuit? No current source. No current source. Now the question is, when there is no current source, how to understand whether a current is entering node 1 or leaving node 1 is the question. You have to understand this very clearly. There is no current source. Understand that? There is a very important rule that we follow in node analysis. Okay, everybody should understand this. Very important note. If you don't understand this, there's nothing understanding it, just remembering and following it. Okay, everybody make a note of that. Very important rule. I'm writing it now. Very important rule. What is that? See, rule. Very important. What is it? Unless there is a current source. Everybody understand? Unless there is a current source which shows current entering. Unless there is a current source which shows current entering a node, we should say a node. Entering a node. Entering the node. We consider all the currents to be leaving the node. Everybody get this point? Read it again. Unless there is a current source, mind you, unless there is a current source which shows the current entering, okay, we consider all the currents to be leaving currents. Very important. Okay, no current source showing the current entering, then all currents are leaving currents. See here, currents are leaving. Okay, currents to be leaving. We consider currents to be leaving. Okay, if no current source, if no current source shows entering current. Okay, very important rule. Now we understand there is no current source. There is no current source. That means the currents that we write now, they're all leaving currents. It's understood. That is what is the convention that we follow. What is convention? That is something that we used to do. Okay, so everybody concentrate. Let's take node 1 separately and node 2 separately. Understand how we apply KCL, then see the two equations, okay, in combined. In combination, we shall see that. Now, let's take just node 1, okay. Anyways, can you tell me node 1, do you have any entering current at node 1? Do you have any entering current at node 1 according to this rule? See, in node 1, we don't have any current sources connected. These how many branches are coming at node 1? There are 3 branches. This is one branch, this is second branch, this is third branch. And in no branches, there is a current source which shows the current entering. What I mean is this. See here, what I mean is this. If there is a current source like this, which shows the current entering this node 1. If there is no source like this, you should understand that the current is leaving. Everybody is okay with that? Okay. So now let's consider node 1 separately. Consider everybody. Write this everybody. Consider node 1. You shall consider only node 1. Okay. So how is this going to look like now? I needed space. Let me write it here. I'll bring the same circuit there. See here, I'm considering just node 1. Only this node I'm considering. Okay, this is the node I'm considering now. Fine. So how does it look like? How does it look like if I take that separately? See, I've got this. Okay, I've got this. Fine, which is ground. Fine, I've got this. Okay, can you tell me what is this? What is there here? There is voltage V1. Okay, if this is this point, if this point is this point, this resistor is what? This resistor is R1. Okay, and what is this resistor? This is R2 and this is R4. Fine, it's not only that. On the other side of this terminal, what is there? There is voltage VA, that is plus VA because it is connected to plus terminal. Understand? Similarly, on the other side, it is plus V2. See, if it's just that, it's just plus V2. It's plus V2. It's plus V1. So this is how we consider node 1. Which is node 1? The node where the voltage V1 is marked, that is your node 1. As we used to consider mesh 1, mesh 2. The mesh where we mark our first current, that is our mesh number 1. Okay, so this is what I'm considering now. This is what I'm considering. Okay, how many currents? How many currents? How many branches there coming at node 1? Anybody? There are 3 branches. Okay, there are 3 branches. Okay, if there are 3 branches, okay, there should be 3 currents. Among the 3 currents, how many are entering, how many are leaving? The questions that we need to be asking ourselves. How many are leaving, how many entering? Okay, now no current is entering there because there is no current source showing the current entering node 1. We consider all the currents to be, see here, leaving. This is leaving, this is leaving, and this is also leaving. Let's say this is our first current. Okay, this is our second current, and this is our third current. or let me write it this way. Let me call this as I1, I2, and I3. Or since it is R4 is going, look, let me write this as I3, not a problem. All the three currents are leaving. Okay, since there is no KCL at node 1, what does it say? Now KCL at KCL at node 1. What is KCL at node 1? It can be referred to as there are three statements which we can follow. One is algebraic sum of currents entering the node is 0, or algebraic sum of currents leaving the node is 0, or the third form is the sum of the currents entering is equal to sum of the currents leaving. Get that point? Now, since there is no current entering, okay, sum of all these leaving currents would be equal to 0, since there is no entering current. Okay, so in that sense, what we can do is this. So there are three currents and all the three currents are leaving. So sum of these currents is going to be 0. So what is that? So it is I1 plus I2 plus I3. Okay, so sum of all these would be 0. Why this is going to be 0? Okay, why this is going to be 0? No entering current. That's why the right hand side is 0. If there were entering currents, I would have taken sum of the leaving current should be equal to sum of the entering currents. Since there is no entering current, it's 0. Right hand side is 0. Okay, now these currents I need to express in terms of the resistors and the voltages. Everybody observe now. If you just understand this much, this is what you have to do regarding the node analysis. So you can solve any problem if you understand this. So concentrate, everybody. See here, see here. What is I1 now? What is I1? See here, I1 is here. I1 is here. I1 is leaving node 1, right? So when I'm operating at node 1, I consider voltage at node 1 as the positive voltage. Everybody is okay with that? Okay, when I'm operating at node 1, I consider this voltage V1 as positive voltage. Okay, similarly we used to do the same in mesh analysis, right? Okay, whichever the mesh I operate in, I take the current in that particular mesh as the positive current, and the current in the other mesh would be negative in that particular KVL. Now in the KCL, wherever I apply KCL, okay, the node voltage at that particular node is considered as the positive voltage. Okay, so what I can do now, what is I1? I1 is leaving, so that means what is current? When would there be a current flowing? When would there be a current flowing? When V1 is equal to VA, there will not be current flowing. When V1 is equal to VA, what is the current? It's 0. When V1 is equal to VA, the current is 0. When would there be a current flowing? When there is potential difference. When there is potential difference, the current would flow. Understand that? Now, since I1 is leaving V1, I consider V1 as positive. Okay, and I write my I1 as, see here everybody, I write my I1 as V1 minus VA by R1. V by R is the current, isn't it? V by R is the current. That's why it's V is what? V is V1 minus VA. Okay, divided by R. What is the voltage difference? Voltage drop across R1. The voltage drop across R1 is V1 minus VA. Why not VA minus V1? Why not VA minus V1? Because I'm not applying KCL at node A. I'm applying rather at node 1. That's why I consider V1 as the positive one. So similarly, can you give me I2? Can you give me I2? Anybody just unmute and tell me what is I2 going to be like? Anybody? What is I2? Seeing I1, what can you say I2 is equal to? I2 is
V1 minus V2 by R2.
good. It's V1 minus V2 by R2. Anybody else who would like to give me R I3? I3, anybody else? The voltage here is 0, mind you. Go on, go on. The
V1 by
voltage here,
R4.
huh?
V1 by R4.
V1 by R4, very good. Why it is V1 by R4? Because it is V1 minus 0 by R4. So V1 minus 0 by R4 is V1 by R4. So you can just If you want, you can take this V1 minus 0. Okay, so the sum of all these leaving currents, they're all leaving currents, mind you. I1, I2, I3 are leaving currents. So sum of all these leaving currents should give you 0. So this is, we have to bring it to the standard form. We have to bring it to the standard form. Let's not do that standard form exercise. Okay, that's something which anybody can do. So this is my equation number 1. Okay, how many unknowns are there? How many unknowns are there? See here, how many unknowns are there? Do we know V1? No, I don't know. Do we know V2? No, I don't know. Do we know this? Yes, I know. So there are just two unknowns. So two unknowns, one equation, not possible to be found out. Okay, so what you need to do, if you have two unknowns, you need to have at least two equations. Okay, so one equation we've got by applying KCL at node 1, the other equation we would get by applying KCL at node 2. Okay, so let's consider node 2 now. Everybody copy that down fast. Consider node 2. Do that, everybody, fast. Consider node 2. Very important. Okay, let's again, if you see node 2 here, again there are three branches. One branch is consisting R2, the other branch consisting R3 and VB, and the third branch is consisting R5. So let me write that here. Let me write that here. Okay, so this is one resistance, this is the other resistance. Okay, and this is the third resistance. Now everybody just observe here, this anyways is ground, and this is my R5. Okay, this is V to my node 2. Okay, voltage at node 2. This is R2 and this is my R3. Everybody, okay, if you are copying and not listening to me, see here, and then you can go on with what you're doing. Understand, this is your V1, mind you. This is your V1. This is plus V1. Okay. Now, can you tell me what is the voltage here? What is the voltage here? What did we say the voltage here is? It's plus VA,
Minus
we told.
V2.
Yes, it's
Minus
minus.
VB.
minus
Exactly, good. See here, at this point, the voltage is plus VA. Okay. Similarly, at this point, the voltage is minus VB. It makes a lot of difference. Makes a lot of difference. So you should understand this is minus VB. Get that point? So this is what is tricky about this particular circuit. Okay, I made that minus plus. I changed the polarities purposefully because I wanted to know I wanted you to know that. Okay, I'll copy this. Okay, and you can just start going. Again, we have three currents. You can name those currents by different names. Can name those currents by different names. We already have named I1, I2, I3. You can take that as I4, I5, I6. You can take that. Okay. So let me, again, all the three currents are leaving, mind you. Why all the currents are leaving? Because there is no current source showing the current entering at node 2. So in that sense, again, these currents are leaving. See, here is the leaving current, here is the leaving current, and even this is a leaving current. Fine. So let me call this as I4, I5, and I6. Okay. So what we're doing, KCL at node 2, we should say. It's not KCL at V2. We are applying KCL at node 2. How many branches? Three branches. How many currents? Three currents. How many entering? How many leaving? All are leaving currents. That's why sum of the leaving currents is equal to 0. So KCL at node 2 very clearly says that I4 plus I5 plus I6 is all, the sum of all this would be 0. What is I4 now? You can you just write it yourself. I'm writing it here anyways. Okay, you do it yourselves. Don't look into what I'm doing. Okay, those who have not followed can look here. I4 is the current leaving node 2. So since I'm applying KCL at node 2, my V2 would be positive. Okay, so it is V2 minus V1 by R2. So it's V2 minus V1 by R2. Okay, plus I5. I5, everybody understand here. V2, it's V2 minus of minus VB. Very important. Here I am writing minus of minus VB. Okay. But you should understand we can write it as V2 plus VB. Okay. Divided by R3. Okay. Then you have V2 by R5. It's V2 minus 0 by R5. So this is your second equation. Anyways, we have to bring this to the standard form. So when we solve the problem, we shall do that. Here you should understand that we wanted two equations because there are two unknowns, and this is how we obtain our unknowns. Is everybody okay with that? Fine. This is type 1 problem wherein there are no current sources. What let's consider type 2 circuit as a circuit which involves the current source. Okay, so let me just take that fast. Okay, so type 2 circuit. Type 2 circuit. In type 2 circuit, what's happening? Current source is present. Current source is present. Those who have not given your attendance can give it now. Current source is present. Where is not a question. Where it is present is not a question. Whereas in mesh analysis, it was a concern. Okay, we had to understand what if it is present on the boundary, what if it is present in between the two meshes was the question that we used to ask in mesh analysis. But here, the position of the current source present is not at all a problem. Okay, so let's understand this now. See here, let's take a simple circuit. Okay, it is this. Yeah, this is the circuit. Fine. Let me call this as a plus minus, and let me mark this as current. Okay. So this is R1, R2, and R3. Can you tell me how many nodes are there? Can you tell me how many nodes are there compared to the previous problem? Just make that analysis. How many nodes are there? So if you have to analyze that, we can see we can write this at this is anyways ground. You don't count your ground. Okay, non-reference node. You tell me. See, this circuit can be written as this is R1, this is VA. Okay, this is R3. Okay, there is a resistor. Okay, there is a current source. This is how the circuit is. Okay, so there is just one non-reference node. This is anyways ground. Understand that? Okay, and the resistor R2 is redundant. Resistor R2 is redundant, not of any use because it is in series with the current source. Okay, so now how many branches are there? Let me call this as V1. There is just one node, so I'm marking that as node 1. Okay, so let's apply KCL at node 1. KCL at node 1. KCL at node 1. What is that KCL? How many branches? There are 3 branches. This is one branch. This is the other branch. This is the third branch. How many entering currents and how many leaving currents can you tell me now? How many entering, how many leaving? 2 leaving, 1 entering. So sum of 2 leaving currents should be equal to the entering currents. Okay. So I'll not write the I'm not marking anything here now. Okay, I'm not marking anything. I'll just write this is V1 minus VA by what? R1 plus V1 by R3. So these two are leaving currents. V1 minus VA by R1 is this. V1 by R3 is this. Understand that? V1 minus VA, V1 by R3. So what is the current here? It's the entering current. R2 is of no matter to me because this is redundant since it is in series with the current source. So what is the current that I'm getting? It is IA. So sum of the entering, sum of the leaving currents is equal to sum of the entering currents. So this is how we see it. Understand? There is type 2 circuit also. There is type 2 circuit also. What is type 2 circuit is all about? Type 3 circuit. Type 2 circuit is presence of current source. Type 1, no current source. Okay. In type 3, what's happening? In type 3, what's happening is there will be a voltage source, but in between the two nodes. There will be a voltage source, but in between the two nodes. So that's a super node problem. As we used to see super mesh, right? When do we form a super mesh? We form a super mesh. I'll show you. We form a super mesh. Is it a super mesh problem? Yeah, this is a super mesh problem. See, we form a super mesh when there is a current source between the two meshes. So when do we form a super node? We form a super node if we have a voltage source between the two nodes. If we have a voltage source between two nodes, so we combine those two nodes to form one super node. Okay, so that we shall see in the next class.